Hey guys, today we are going to begin our work on vectors. So the first two words you need to understand for vectors is scalar and vector. Now, these are both measurements essentially, but the scalar has magnitude, so this one has magnitude, but no direction. Has magnitude. I'm going to zoom in so that my handwriting is neater. And no, I'm off to a good start. I messed up on the third word. Okay. No direction. Okay. All right, so the difference is a vector has magnitude and direction. So it has a number associated with it, but it also tells you which way it's going. Magnitude and direction. And that's important because that's the only difference. All right. So not surprisingly, vectors is what we're working with primarily this for the rest of the course. Given the name of the course, that should be obvious. But anyway, so if we look through some of these different things here, so time, for instance, time doesn't have a direction. It's just how much time has gone by. So that's going to be a scalar. Okay. Position, it tells you, that's a funny one, but it's going to have a number, but it's also going to tell you where it is. So that's going to be a vector. Okay. Temperature doesn't have a direction. Electric charge, as far as I know, doesn't have a direction. Okay. If we jump over here to mass, you have a set amount of mass. Like it's not, it's just a scalar. It's just a scalar. Force, on the other hand, is like you think of the force of gravity. Well, the force is set amount, but it's also pulling you down, and that's important because that's different than if the force was pushing you up. So that's going to be a vector. Okay. Displacement, also a vector because it's going to tell us not only how far we are from something, but what direction we are from something. Okay, and finally age, which is the same thing as time. So I don't know why those are separate, but that's also a scalar. Okay? All right, so we got four different types of vectors we're going to talk about here. The first one is a geometric vectors. So this is these are vectors not related to any coordinate system. Okay, so not, my pen stopped working. There we go. Not related to any coordinate system. System. All right. So for instance, I would just actually draw, A to B, and I talk about the vector A, B, like that. That little arrow on top is what tells us that it is in fact a vector. Okay. So then let's jump down to position vector here. So this is a directed line segment from the point of the origin to a point. So we'll say directed line segment. Which we're going to call OP, okay, because it'll go from O and go to P, from the origin to a point P. All right, so what's significant about these here is and we can see this in A. So this would look the same. It would just be on an axis basically. So you'd have something like that. That's P. Okay. So that's it. Whatever. So and then that would be O, obviously, because that's the origin. So it's O, P. So you can see the way that we've the angle that you've drawn it, the direction it's pointing, that's your direction that we're talking about here. And then your magnitude is how long the line is, okay? How far, and for the position vector, how far it is from the origin. For the AB there, it's just the distance between A and B, okay? So, let's jump up to algebraic vectors. Okay, so these are vectors related to a coordinate system, okay? Related. Well, I'm having troubles with my pen today. related to a coordinate system. Okay. So these are going to be described by their components within the system. So described by components. Described. Whoops. That's getting my B's and D's mixed up. I'm back to grade 1. By their. Oh my goodness. You can't see this, but this pen that I'm having a hard time with is built out of tin foil and a Q-tip, so it's not really it's surprising that this isn't working well. So anyways, described by, their components, we'll say. Their components. I think we already said that. We did. I know we already said that. All right, so the way it would look is, for instance, if I'm drawing a vector v, I would write it either, there's two ways we would do this. I'll say 1, 2, 3. So obviously I'm writing that one as one in 3 dimensions, okay? But you would write it in brackets like that, just like you're pointing a coordinate, writing a coordinate, but then you put an arrow over top, okay? And that shows that it's a vector. The other way you can write it, that you will see, not so much this year, but you will if you continue on in this stuff in university, is you'll see it written like this sometimes, okay? Those are 2 ways to write it like that. Okay. And then finally, the last one. Now it's written as. Oh yeah. Okay, sorry. Okay, so we got a displacement vector. So this is the directed line segment from the point A to B. Okay. Directed line segment. From point A to point B. And this one we would also write as AB, like that. So it's just telling you it goes from point A to point B. Okay? All right. So I'm going to quickly do these ones with you, although my lines are going to be really crooked. Okay? But the position vectors, so the idea of a position vector is we're always just starting from O. So O to A, just go like that. Oh, pen problems again. And there. Make sure you put your arrow on it. So that is O. Oh my goodness. O, A. There we go. Okay. And OB obviously would be to there, and OC would be to there. So that's OB. And that's OC. Not terribly complicated. Okay? If we draw the displacement vectors, PQ and RQ, so again, we're on a grid here, and so I go P to Q, and we go R to Q, okay, for RQ. All right, so the only difference between those two is that this guy over here, you always have to start this one, that one. You have to start at the origin, and for displacement vectors, you just start wherever it tells you to start. Okay. All right. Let's see. So Pythagorean theorem. Now you learned Pythagorean theorem a long time ago, but what you didn't learn is that there's actually more to it. So first of all, what you are familiar with is the two-dimensional version, which the magnitude of A to B. Okay, remember the Pythagorean theorem will only tell you the magnitude. It's not going to tell you the direction, but it'll tell you the size of a line, the length of a line. Okay, but you're going to have A squared plus B squared, and then we square root it. Okay, so that's just your basic Pythagorean theorem. But what you may not have known is that it also works in 3 dimensions. Okay, so if I was doing, I didn't specify, but I was referring to this diagram right here. So that would be going from A to B. That would tell you that length. If we go over to this guy here, if I want to go from A all the way to G, way in the far corner, well, it's going to work basically the same, except we've got more coordinates. Okay, so AG is going to be the square root of A squared plus b squared plus c squared. Okay. So yeah, it's I don't know. I don't know why we don't show that it works in 3 dimensions earlier, but we do, or we just did. So there we go. Now you know. Knowing is half the battle. All right. So the magnitude, what the magnitude is the length or the intensity of the vector. The length or the size, I guess I could say too. The length. Spell it right. Size or whoops, that says oof. Anyway, the intensity. Intensity. See if I can spell it right. Of a vector. So to show that you are talking about the magnitude, the way you'll write it is you'll write the name of the vector. Whoops, I did not mean to switch to green there. You'll write the name of the vector. So if we're just talking about vector v, for instance, we would put absolute value around it to show that we're talking about the magnitude. Sometimes you'll see it with a double. I think your textbook might actually do this, where it does it with a double, and that's acceptable too. You will see people just drop the arrow part. Like, oh, sorry, I just drew the arrow part. You'll see people just drop the arrow part and write the v. That's less common, and some would argue it's less correct, but, you know, whatever. Whatever. It works. Whatever works. All right, let's jump over to the next page here. Sorry, I'm taking a little long on this one, but... so the first 2 examples there, I'm actually going to have you work through in class, and we are going to jump ahead to these guys right here. Okay? So, equivalent or equal vectors. So, equivalent or equal vectors, they have the, whoops, not writing again, they have the same magnitude and they have the same direction. If you have the same magnitude, same direction, then those vectors are equal. Okay? It doesn't matter where they are. So for instance, over here I got AB and I got CD. Those are equivalent. Okay? The fact that AB is above CD is irrelevant. The magnitude's the same, the direction's the same. Those are equal vectors. Okay? Opposite vectors have the same, oh my goodness, it's not working at all. There we go. Same, geez. Same magnitude. Okay, I just dotted my U. Oops. Okay, but what is different is that the opposite direction. They have the opposite direction, exactly the opposite direction. Okay. Not different direction, opposite direction. It has to be going exactly the opposite direction. So for instance, we've got A to B here and C to D. They're exactly the same, except that the direction is going exactly the other way. Okay? And that makes them opposite vectors. Okay? Parallel vectors have same direction. Same or opposite direction, I should say. Same or opposite direction. And the magnitude is irrelevant. Okay? So there's a couple of them there. Those are all parallel. All right? They'll look like parallel lines. Okay? All right. So, last thing I'm going to do with you, and then I can get you to do the examples yourself. We're going to talk about direction, the way we write some of these direction vectors. Okay? There are 2 major ways of doing it, the true bearing or azimuth bearing, and then the quadrant bearing. Now, you will see the true bearing more in a math class. Typically, quadrant bearing, I believe, is more what you'll see in a physics class. Neither one's really better than the other, but I do think quadrant bearing is probably more common, to be honest with you. But I like true bearing. I just like azimuth. I don't know. I assume that's a guy's name, but I don't even know. So anyway, the direction is given. Direction is given, okay, by the angle between north and the vector. By angle between north and the vector. And you do always have to go clockwise for this. Always clockwise. All right. So for instance, here we've got this guy here. The angle starting at north going around to the vector was 120 degrees. So we just put square brackets next to our measurement and write 120 degrees. If there's no directions given, you assume that this is a true bearing. Okay? If, however, it is a quadrant bearing, it's given between the north-south line and the vector. So it can go from the north or from the south. Okay? And then you just have to specify whether you went to the east or to the west, or from the north or from the south. So, so we'll say angle between north or south in the vector. Okay. Specifying east or west. Okay. So for instance, this one we started at north, we went towards east 45 degrees, so it says north 45 degrees. Similarly, I could have had one, if I had one over here, okay, I would say south. Oh, I'm almost done and my thing's just not working at all. So I would say south, and let's say it was 45 degrees, and I was going towards west. So you just specify, what's that shit, and always square brackets. You just specify where you started, right there, and then you specify which direction you went right there, and then that's just the angle that you went. Okay, and that's it. All right, so I'm going to get you to do the examples in class. So until next time, go Sabres.